Okay, today we're going to talk about how NMR actually works. Right. Now, protons, like electrons, can exist in two spin states. Okay, they can have an upspin shown there, or a downspin. Now, if it has upspin, the proton behaves as a tiny bar magnet with its polarity that way around, with the north pole at the top there and the south pole there. Whereas if it has the other spin state, the downspin state, then it behaves as a bar magnet, but the other way around, with the south at the top and the north bottom. You can probably see that, you can probably appreciate that it doesn't really care which way round it is most of the time. The energy of having the upspin or the downspin is going to be the same. But that won't be the case if you put your protons in a magnetic field. Okay, so here's an external magnetic field here, north pole of the magnet there and south pole there. Let's draw in the two. So there's the one with the upspin and there's the one with the downspin. That is going to have the polarity that way around. This is going to be that way around. Now you can see that this one here is going to be slightly higher in energy. It's not going to like being this way around, because the north pole is going to repel the north pole of the external field, whereas this state is going to be lower in energy because it's going to want to go that way around, because the south pole is attracted towards the north pole of the external field. Okay. If you want to, you can flip the magnet. You can change the energy state. But if you want to go from from this lower energy state to the higher energy state, in order to flip the proton the other way around and reverse its spin, you're going to have to give it some energy. And that energy can be provided in the form of an electromagnetic wave. Now, you've probably come across this expression before, but the energy of an electromagnetic wave is given by a constant, h, Planck's constant, multiplied by the frequency of the radiation. And this is the frequency. Okay, and if this is the external field is going to be provided by a very strong electromagnet, and if in the range magnetic field strength used by the spectrometer, the frequency of the radiation it absorbs is in the radio part of the spectrum. So it's not, as you know, that radio waves have quite low frequency, so they've got quite low energy as far as electromagnetic radiation goes. Okay, let's see how NMR, let's just have a look at this diagram then, yeah. Right. Right, what I'm trying to show here is as we go from left to right here, you can see we have increased the increasing the magnetic field strength. Okay, and on over here, this is when you've got zero magnetic field strength, and you can see these two energy levels shown by horizontal black lines. For the upspin and the downspin, the energy level is exactly the same. The proton doesn't care which way around the magnet is. If it's got upspin or downspin. As we increase the field strength up to this one here, then you can see that the energy starts the energy between the two states starts to get a little bit bigger. Okay, and as you increase it, it gets bigger still when you get to here. Okay. Now, all the time, if we think of our little sample here, what we've got our sample of compound that we're interested in, and it is in a external magnetic field, and we're increasing the strength of that. And all the time, shining through that sample is a radio wave. So we're showing green there. So that's the radio wave. And the energy of the radio wave I've shown on this diagram as that little green bar. Okay, so you can see this green bar here. This is the energy of that radio wave. So at first you can see that obviously there's no energy separation between the two states, so nothing happens there. As you increase the field strength a bit more, the energy level gets bigger. But the energy level here, the energy separation is not as big as the energy of the radio wave. The radio wave's got too much energy to promote that proton from that energy state up to the higher energy state. That doesn't happen there. However, as the separation gets bigger, you can see that the energy of the radio wave is now exactly the right size to promote this proton up to the higher energy state. So it will absorb the radio wave there. Here, the separation is now too big. It's bigger than the energy of the radio wave, so you can't use that to promote the proton from the lower state to the higher state. Likewise here, it's too big as well. Right, just rub this out, and then I'm going to draw on this axis now. So this is going to be the absorption of radio waves. And along this axis, red, we're increasing the magnetic field strength. So you can see here, no absorbance of radio waves at all, because the energy of the radio wave is too big for the gap between the two energy levels. And that will carry on until we get to here. And here, the separation of the two energy levels is exactly the same as the energy of the radio wave. So the radio wave now will be used to promote that proton to the higher energy state, and so you'll get an absorbance. Then as you increase the field strength even more, the radio wave will stop being absorbed because the energy separation of the two states is bigger than the energy of the radio wave, and that will carry on there all the way along flat. So you can see you're going to get one peak of absorbance of radio waves, and so but we're only getting one peak, whereas we know in a spectrum you get lots of different peaks. Well, the reason why you get lots of different peaks is because the experienced field is not the same as each proton doesn't feel the full strength of the external field, because the external field is shielded or blocked by electrons. So the more electrons you have got surrounding a proton, the less it will feel the external field. So it'll only feel it might be only feel 99% of the field. Okay, the other 1% is blocked by the electrons. And of course, each proton environment has different amount of shielding by electrons, and that's why each proton environment will give you a separate peak. You get a separate peak for each proton environment. You don't just get one peak, and that is called chemical shift, as we know. It's usually, and it's measured in parts per million. and it's caused by different protons having different numbers, different electron densities around them. The electron density will block the external field, and as we know, if you're near to an electronegative element, that tends to withdraw electrons away from the proton, so it feels more the strength of the external field. So that proton is de-shielded, whereas the ones down here, like TMS, which is very highly shielded, they've got lots of electrons around each proton, so you need a bigger external field in order to cause the same energy separation. Okay,